Right, addressing modes. It's how the control unit interprets the operand part of an instruction. An instruction's made up, and this we talked about this already, of two parts. So for every instruction you get an opcode, which is a certain number of bits, followed by an operand. So the opcode is what is the instruction. Remember, these are just binary numbers, okay, and we're like putting abstract terms on top of these. The operand is the data that you need for that instruction. Obviously, some instructions don't need data. So if you've got a NOP instruction which says just perform a fetch exit cycle but don't change anything in the CPU, that doesn't need any data. If you've got a halt instruction which just says just wait for an interrupt, mate, that doesn't need any operand. Okay, but if we want to add numbers together or load a value to a register, then there is data involved. Where does that information come from? That's what the operand is. So the operand is actually two elements: an effective address and the data. Okay, so there are two parts to that. So how to interpret the data, that's what an effective address. And we call this an addressing mode. So our point of reference currently is little man computer. So when we have little man computer code, we might have an instruction like this: LDA 45. So what that meant was load a value to the accumulator, but get it from address 45. So the addressing mode, and this has got a name, this addressing mode, this is what we call direct addressing. And this is where the operand is a memory address, where the data is. So the operand is a memory location. And if you want to think at a high-level language definition, this is what we would call, when we're coding, a variable. That's what a variable is: a memory location that references a piece of data. But obviously at the CPU's level, it don't care about names of stuff, it just wants to know where it is. Interestingly, when we're writing Python C# code, we actually are in the opposite camp. We go, oh, I don't care where it is, I just want a name to refer to it. I don't care where you've put it, that's up to you. But the CPU doesn't deal with our stuff, it deals with its low level. So this is the equivalent of a variable. So that's what we've seen. Okay? So we look at the operand, we go, okay, it's an address, put that address in the memory address register. Okay? What I'm going to do is I'm going to run through what the modes are, and then we're going to look at examples and see how they're executed. Okay? Right. And that's as far as Little Man Computer goes. And that's why Little Man Computer is a real pig to write any code for, because it's only got variables. And you think, oh, that's all right, it's got variables. But it hampers us. The more useful addressing mode that it's missing is the next one, which we might write a mnemonic like this for. This is called, and you'll understand why, immediate addressing. And this is the simplest addressing mode, because what this tells the control unit to do is it says, you know what, the operand, that is the data you want. The operand is the data. So in this case, the 45 is the actual number 45. So I want to load, and this is what, you know when we was doing that thing the other day and we wanted to like make a counter, and we wanted to load a count value to an accumulator, and we had to like have a counter stored in memory somewhere called count, and put a number in it, and that's what number got loaded. Well, really what we wanted to do was be able to say LDA #1 to load a 1 in there, or load a 0. So this is super useful. So the operand is the data, and in high-level language terms, we would define this as a constant, because it's fixed in the code. That code is fixed. Every time I run that code, it will load the value 45. If I look at the previous addressing mode, direct addressing, it's not fixed. 45 is a location. The value in that location can be changed. Okay? So this is what we would call a constant. Bad practice in assembly language to use literals like that. You would use symbols to represent those constant values, which you will see when we get on later in the week looking at some proper assembly language. Okay, so that's the constant. They're the basic two. Don't mix up direct addressing with immediate. I've messed my E up there, haven't I? People get that mix up. Direct means directly the location. That's where the data is. These are just generalized addressing modes. In real CPUs, you have registered direct addressing, where the location is a register where you'll find your data, which makes sense when you've got lots of different registers, as you will see. Okay, the next addressing mode. We might write the assembly language for it like this. This is weird. You must not go on an infinite recursive loop when you think about this, and I'll tell you in a minute. Right, so this is called indirect addressing. It's got another name though, which is a bit more sensible. Or what we call vectored addressing. But the example we'll use indirect. Right, now this is a bit more complicated to explain. It's actually easier to understand than it is to explain. Okay, right, so this is where the operand is an address. Inside that address, so at that location, is an address. So we've got an address of an address. That's why it's called indirect. Okay? That address is where the data is. It's only two levels. Don't like go an address of an address of an address of an address of an address. It's not that. The final address is the location of the data we want. You use this quite a lot, okay, for things like jump tables and decision tables, so that you don't have to do any logic. It's also used for interrupts. So a hardware manufacturer may specify that at a certain location in memory, say location 0, when the vertical blank interrupt, so like the screen has just finished drawing interrupt occurs, it will go to that location and it will load an address from there. That is the address of a routine that needs to execute. So you've got an address of an address. And the reason they do that is so that it can be changed in software. If you've got a location that's fixed, but its content can change, then that means you can change what happens when you go there. We use this for drivers. So when you've got a mouse driver, if you want to write your own mouse driver, you can update the interrupt vector and say, don't go to that code, go to my code. If you want to write a keylogger, so you can steal everyone's information, what you're going to do is you're going to overwrite the keyboard interrupt service routine. You're actually going to call the actual keyboard interrupt service routine, but after you've done what you want to do with the data that's coming from the keyboard. That's what keyloggers are. Okay? If you want to create logical devices like virtual disks and virtual Blu-ray players and things like that that pretend they're a piece of hardware to the operating system, you're using indirect addressing, vectored addressers. So that's interrupt, handlers, device, drivers. So that they can be changed. Because if it was fixed, it wouldn't be very good. So anything where you've got like a fixed location, but you want to be able to update things. But we also use it for jump tables. So you can do, you will find when you're writing games or simulations and things that what you might use is what we call a state block, where you can be in different states and you need to perform different actions based on a state. So it may be that your character is standing, so they do something. If they're climbing, they can't go left and right, and they can only go up and down. They may be throwing, they may be sliding, and they're all in these different states. So what you do is you kind of do like an if it's this state, do this, if it's this state, do this, etc. Okay, which is time consuming. So what you tend to do when you're doing low-level programming is you will go, well, I'll keep track of what state I'm in, and I'll use some sort of jump vector to go to the location. So I won't do any calculations whatsoever. I won't do any testing, don't need to. Okay? It's the hardest one for you to understand. But it is an address of the address of the data. Okay? Right, the next one is the one that makes everything make sense when we're talking about accessing arrays and everything. So the next one might look something like this. This is what we call indexed addressing. Now, there are loads of different real addressing modes that are similar to this, as well as just indexed addressing, where we have two values that we combine together. So the operand, in this case, is two values. It's an address, but it's made up from a base value and an offset. Where I've presented that LDA X, 1000, which one of those do you think is the base value? The 1000. X is the offset. Okay, I can vary X. So whatever the value of X is, that is added to the 1000. This is just an example, we're abstracting. Okay, how these work in principle is different in different assembly languages and for different CPUs. But we're basically getting the address of the data by combining a static value with a dynamic value. Now this is perfect for accessing arrays. or tables. It's quite interesting. Some CPUs have some really good instructions and things for accessing tables that might be with entries that are 1 byte, 2 byte and 4 byte. It can automatically like multiply and things like that. This is what we call an index register. Okay. So where you have something in memory like this, just as a quick example, if I set the base, if I say LDX hash 0, so set index register to 0, and then I do this, LDA X1000, what value do you think is going to get loaded to the accumulator? D. I'm accessing an array, string, effectively. I've specified where that string is in memory, 1000, and I've said index 0. This is why all things start at 0, because of index addressing. Okay, so the first item in an array is at position 0, because you would access it by setting the offset to 0. If you want to get the second item, you set the offset to 1. So you might have something like this. And you can see you can then nicely process that in a loop of some description, if you know how to do loops in assembly language. They should have had all these in Little Man Computer, I think, because you could have done some really cool stuff. You could have done string output and all sorts of weird things. Right, so we can use the index register to step through an array. Fundamental to a lot of algorithms accessing arrays. Okay, and this is the fellow that can help you, the indexed addressing. Anyone got any queries about that? Right, what we need to do to get this nailed down is just have a look at a couple of examples. I'll do one example of each and show the fetch execute cycle in operation. Okay, so I'll stop that video there so we don't go on and on.